Good afternoon, everybody, and welcome to another Geo-Institute live stream. My name is Brad Keeler. I'm the director of the Geo-Institute, and we welcome you to Geo-Extreme Preview number 2. If you don't know anything about the Geo-Institute, after you watch this presentation today, head over to geoinstitute.org, and there you will find out all kinds of things about us, including that we are a technical society with about 12,000 members. If you don't know anything about technical engineers and or geologists, and that we are part of the American Society of Civil Engineers. And if you like what you see today, and I think you will. I mean, I always think you will, but I wouldn't lie, viewers. You should click like, subscribe, and get notifications, and we will let you know every time we post something to the YouTube channel. Now, those of you who are of a certain age will remember a certain Seinfeld episode where the theme was worlds colliding. Today, we have our geotechnical history blogger, and we have the Geo-Extreme preview coming together in an unholy union to provide you with one of the most exciting, immersive, dare I say, extreme geotech experiences that you have ever had. This is going to be fantastic. From the Geo-Extreme Program Committee, here to host and moderate and do all that amazing stuff today, all the way from the suburbs of Philadelphia, Pennsylvania. It is Jay McKelvey. Jay, welcome. Thanks for doing this. Tell us about the conference and then tell us what everybody's going to see today.
Oh, thank you, Brad. So, hey, everyone. So Geo-Extreme 25 is actually a follow-up conference to the first one that was in Savannah in 2021, actually the first GI conference after COVID. So it was highly successful because there was a bunch of engineers just dying to get out. It's a slightly different format than if you've been to a typical GI conference. This is multi-disciplinary. So we've got climate scientists, engineers, emergency managers, resilience and sustainability. We got insurance experts and policymakers, and with the focus on how to handle man-made and natural extreme events. So we'll be focused on hurricanes, floods, extreme precipitation, droughts, wildfires. Will be certainly discussed following last year's LA experience with the fires. Debris flows is a big thing. Earthquakes under a changing climate. So it's going to be really, really interesting. We've got some good people working on the conference. We got a lot of great papers. Early bird registration is September 9th is the deadline for that. So go to geoextreme.org, take a look at the conference website, and you can sign up for the early bird registration. Okay, so I hope to see you all there. It's going to be a lot of fun. I have the great honor to introduce a fellow Delaware Valley Geo-Institute member, Michael Bennett. Mike, he got his BS in civil from Lafayette College back in 2013. He's currently following up on a master's that he got at Virginia Tech, where now he's pursuing a PhD full time down there at Virginia Tech. Michael's got a PE and has worked with about 5 or 6 different geotechnical firms. So it's a great honor to have him. Mike's the Geotech History blog. So his presentations, I've seen a couple of them, are always interesting, and I'm looking forward to hearing Michael Bennett's talk today on the St. Francis Dam failure. Michael, take it over.
Jay, thank you so much for that kind introduction. I would mention only that I graduated Lafayette in 2017.
Okay.
But if you want to give me the extra 4 years of experience, I will gladly take it. And without further ado, I think I'll just dive right in. You can see that all right, Jay?
Yep.
Perfect. Let's get going. So I'll start today's talk by going over what happened in broad brush strokes in the St. Francis Dam breach of 1928, followed by some background on the event, the growth of the City of Angels and its constant thirst for more water. Then I'll review the design and construction process of the St. Francis Dam. While I'm talking about that, I'll also be discussing where the geotech standard of care for dams stood in the early 1920s. Following that, I'll go over the breach itself, kind of a blow-by-blow of how it played out, and I'll touch briefly upon its terrible human toll. Then I'll look at the aftermath of the disaster, what it meant for the dam's engineer, William Mulholland, how the various investigations into the breach played out, and its connections with the construction of the Hoover Dam and its impacts on civil engineering, licensure, and review laws. I'll talk about some of the progress we've made as a profession since then, briefly review a few modern challenges facing American dams, and then close out by recapping a couple main points. So, on March 12th, 1928, St. Francis Dam, about 40 miles northeast of Los Angeles, failed just before midnight. The immediate cause was uplift from seepage under the dam, but the long-term cause was that the dam had not been geotechnically designed very well. The dam breach released over 1 billion gallons of water into San Francisquito Canyon. It happened under cover of night, and so the wave destroyed or damaged many small towns and killed about 400 people, many of whom did not have the ability to get away because the disaster was on them before they knew it. It remains the second deadliest dam breach in our country's history, behind only the Johnstown flood. Now, the failure was extensively studied at the time it happened and has also been extensively looked at by generations of engineers and historians since then. A couple dramatic factors combined to produce this level of interest, because the failure not only ended the career of one of the West's most esteemed water engineers, William Mulholland, it also led to stricter licensure laws for civies and increased scrutiny of dam safety. And to this day, the disaster carries powerful lessons for all of us in civil engineering, especially we geotechs. So, Los Angeles in 1885 was just a small coastal town with a population of 11,000. San Francisco was the dominant metropolis in the Golden State. But that all began to change as the Gilded Age turned over to the Progressive era. In 20 years, by 1905, the city's population had swelled nearly 1,800% to more than 200,000 people. And therein lay a problem, because, as has been said elsewhere, nature has not provided California with the right amount of water in the right places at the right times. And the solution of that was the Los Angeles Aqueduct. It is a 233-mile network of channels and siphons that conveys water from the Owens River in central California down to the City of Angels. It opened in 1913 and supplied Los Angeles with 300,000 acre-feet annually. And the project was brought to fruition by the city's water supply engineer, a political and technical wizard, or at least that was his reputation then, William Mulholland. Here's a photo of what Hollywood looked like at the turn of the 20th century. The movies hadn't yet arrived, and the city still wasn't, that part of the city still wasn't ready for its close-up. So William Mulholland was self-taught, as many engineers at the time were. He had worked for the city since the 1870s and had slowly climbed the ladder rung by rung from a ditch digger on sewer projects to chief of the Bureau of Waterworks and Supply. He was known to his men with some affection and a good deal of deference as the chief, and Mulholland tended to keep his own counsel. He didn't take kindly to others meddling, as he saw it, in his business. Now, the Los Angeles Aqueduct is what made Mulholland truly a national civil engineering standout, but it also made him famous, which led to a degree of overconfidence, bordering on arrogance at times, well encapsulated in a remark he made at the aqueduct's dedication ceremony, where he told the crowd, "There it is, take it." Now, the city's population continued to skyrocket as the 1900s progressed. 1905, as I mentioned, there were 200,000 Angelenos. Just about 20 years later, there were 600,000. There was more population growth coming in all the time, and That resulted in the need for more water. But it also resulted in more problems because farmers in Central California who had depended on the Owens River for their water supply were still angry with Mulholland for taking so much of it. There were actually several dynamite attacks on the Los Angeles aqueduct and some tense standoffs between angry farmers and law enforcement. Fortunately, nobody was killed or injured in these episodes, but it underscored the need for a greater water supply within Los Angeles. The city did undertake several new reservoirs within its limits, most notably the Hollywood Dam, which was renamed Mulholland Dam in honor of its engineer when it was completed. But they still weren't adequate in terms of their capacity. And the only solution was going to be another larger reservoir that was near to the city so that there weren't all these risks of saboteurs. So, natural site quickly became apparent in San Francisco Canyon, about 40 miles northeast of downtown Los Angeles. The site was owned by the U.S. Forest Service, so Mulholland et al. Wouldn't need to use eminent domain to get land. The base of the canyon is at an elevation of roughly 1,650 feet, which gave plenty of head for a water supply system. Now, the site geologically lies along a contact between two formations. Contact runs north-south. On its east side is mica schist. On its west side, friable sandstone. Those are important to the story I'm going to relate today. That contact is ultimately a very dormant fault. That does not factor into the story, but it's just worth observing. The east side of the canyon, with the mica schist formations, is ringed by paleo landslides. That is an important detail to remember. Now, for the St. Francis Dam, Mulholland decided to choose a concrete gravity design. His reasoning remains open to speculation, but it seems likely that it stems from 1918. He had been supervising at that time construction of a hydraulic fill dam near Oakland, the Calaveras Dam, and it underwent a slope failure in a large slide that was professionally somewhat embarrassing. So when Mulholland went to build the Hollywood Dam, now the Mulholland Dam, the crews finishing it used a concrete gravity design. It looked more modern and had a visual potency, as some historians have said, and he decided that he would pretty much reuse the design for the St. Francis Dam. The Forest Service granted him permission to construct it early in 1923, at which point design began. For those unfamiliar with Los Angeles geography, and I certainly was before I started looking into this disaster, you have downtown Los Angeles right around here, and then you have the X marking the spot of the St. Francis Dam, not all that far from it. San Francisco Canyon, rather, is shown here in a picture in the early 1920s from before the dam was built. The sandstone formation is visible on the left side of the photo, the darker material. You can see that contact line, the dormant fault running between them, and the mica schist, lighter in color, on the right or east side of the photo. I've labeled where the dam was going to be built. And here you can see what looks like a firm flank of the hillside, but is actually the remnant of one of those paleo landslides. As one person wrote after St. Francis, once a slide, always a slide. And you're going to see just why that was so. Now, remember, geotech as we know and love it today did not really exist just over 100 years ago. What we had was a jumble of scattered principles, unreliable rules of thumb, and experiential judgment, as well as a deep schism between theoreticians and practitioners on topics related to soil mechanics and foundations. Now, changes were coming to that state of affairs because Karl Terzaghi was hard at work in Istanbul on landmark research on the subject, but it wouldn't be published for another 2 years. However, as of 1923, there were some basic principles that had been well established, enough that that year a book was compiled for the average practitioner, Foundations, Abutments, and Footings. Now, this book, which is not at all a rare one, you can look it up on eBay if you don't believe me, paints a very good picture of where the field was at the time. It was widely available. It was written in an accessible yet technically rigorous manner for practitioners, and I think you can argue that this represents where the field's standard of care was back then. Now, this book contained a detailed section on dam foundations, authored by seasoned dam engineer Charles Paul. And so I think it's quite revealing to compare the guidance Paul gave in his chapter of the book to what William Mulholland did at the St. Francis Dam site. Paul said that the main requirements to be considered for a dam foundation included bearing power, water tightness or control of seepage, and prevention or control of upward pressure uplift. And the failure to understand those conditions or appreciate their importance, he added gravely, has often resulted in disaster. He noted that any masonry or concrete dam more than 200 feet tall needed to be founded on firm, hard rock without open seams, fissures, or faulting. The St. Francis Dam was ultimately going to be 205 feet tall, and the friable sandstone and fissile mica schist below it weren't really ideal for what Mulholland wanted to build there. But Charles Paul recognized that you couldn't pick subsurface conditions at a site. Not every site was going to be ideally constituted for the dam you wanted to build there. And so he noted that a subsurface examination was ever more critical as the material strength went down. He also noted that special treatment would often be necessary so that the dam's foundation requirements were attained. Now, Charles Paul knew very well of what he spoke. A number of his dams still exist to this day. Here's the Arrow Rock Dam in Boise, Idaho, and on the right, Lockington Dam in Southwest Ohio. Paul noted that it was desirable for dams to have a careful geological explanation of foundation conditions, ideally one by an expert practical geologist. Per his account, it was important to assess the bedrock's probability of fissures and faulting, as well as former upheavals and disturbance, such as paleo landslides. Paul recommended gathering soil samples at dam sites using wash borings. A common technique in 1923, put your wash hose in the ground after you drill a boring, and you wash samples to the surface. He added that those were most valuable if they were used together with test pits, which he wrote afforded the only opportunity to inspect material in place. That's still a huge advantage of them to this day. As for bedrock cores, Paul preferred that at least 20 feet of bedrock be cored to assess its character. You had to verify that it was there. You had to observe its quality, whether there were faults, geologic faults, that is, whether there were lenses of soil present. He knew that keenly from his experience at Arrow Rock Dam, where his cruise rock cores had uncovered a soil layer beneath the rock layer. And when Paul and his cohorts thought about it, they realized that there was a buried paleo ledge at the site. That could have severely compromised the dam's foundation had they not found out about it in time. By contrast, we have no evidence that Mulholland considered the site engineering geology for the St. Francis Dam. Now, he did briefly visit the location with Stanford geologist J.P. Branner before the design process began. Today, Branner's probably most famous for mentoring geologist and future President Herbert Hoover, who was actually the Republican nominee and the election winner the year the dam failed. But this quick jaunt to the site hardly qualified as a suitable geologic study. Now, Mulholland had geologic data on the site available to him. When workers a decade earlier had excavated a tunnel through the mica schist for the Los Angeles Aqueduct under Mulholland's direction, they had complained frequently about the formation's hazardous dip and tendency to expand upon excavation, but it's not apparent that the chief ever considered the experience his men had had in this regard. As for the dam itself, the crews took only 4 or 5 borings all along the west abutment, and they extended to an average of 15 feet deep or so. They conducted a crude falling head permeability test in one of the borings, but nothing to the extent or rigor of what Charles Paul had suggested. Here's a shot of those men digging the tunnel for the aqueduct through the mountain adjacent to the St. Francis Dam site in the early 1900s. Now, Mulholland did a little bit more investigative work on the east side of St. Francisquito Canyon, but it probably hurt long into the mica schist to assess its caliber. They said that the tunnel's diameter was roughly big enough for a man to work running a wheelbarrow, and that among the tools used to excavate the tunnel was blasting powder. They didn't backfill this tunnel with concrete until the dam was built years later. Now, it almost goes without saying that excavating a sizable tunnel into the schist with uncontrolled explosives and then leaving it open for a lengthy period of time could only have harmed both the geological stability of the formation and the integrity of the future dam. That's especially true given that mica schist tends to expand upon atmospheric exposure, which is why the workers used to refer to the formation as, quote, heavy ground. It's also likely the case that those blasts and that excavation destabilized the paleo landslides in the mica schist to some degree. As for foundation excavation, Paul noted that the preparation of the rock foundation for a high masonry or concrete dam required that all loose or soft rock be carefully cleaned off and removed. Paul did recognize that some types of rock decompose very quickly upon atmospheric exposure, so he qualified his instructions accordingly. He said that degradation-susceptible rock could initially be excavated to within a few inches of finished grade, and that the remaining material could then be removed just before concrete was placed. Here's an example of what he was talking about at his Arrow Rock Dam. On the left, you can see the large-scale excavations going on, men with pickaxes and shovels. On the right, you can see a worker looking over the finished product, which may not be the most even excavation, but is definitely on solid bedrock without any remaining chips or talus or anything like that. Things were a little bit different when Mulholland began building the St. Francis Dam in 1924. We have fairly good construction records from the project, but the practices reflected in those records were suboptimal. As I've mentioned, an exploratory tunnel was dug into the mica schist, and the fact that that undercut damaged the formation so much, damaged the location of the future foundation so much, was very much contrary to Charles Paul's guidance. As you can see in this photo, talus and loose rock from the hillsides along the future abutments of the dam, this is the east abutment, wasn't properly cleared off before concrete was poured. As for the design of uplift for dams, that was fairly new in 1923, but the novelty was wearing off. As Charles Paul put it, the subject had been under lively discussion for a few years by then, but preventing uplift in dams usually wasn't too complicated. About a decade later, uplift had been thrust to the forefront of dam engineering discussions when a uplift-driven breach in north-central Pennsylvania killed 78 people. Only a timely phone call from a local who lived near that dam, the Austin Dam, spared hundreds more lives. And following the disaster, at least one esteemed American civil engineer declared that it was a crime to design a dam without considering upward pressure. Unfortunately, that wasn't Mulholland. A plethora of literature on the subject appeared in technical periodicals over the next decade, so that by 1923, engineers were still debating how to compute uplift, but everyone agreed that it needed to be considered and provided for. As to how to provide for it, Charles Paul had a couple ideas. The first one we talked about was subsurface grouting, which he called standard practice in the construction of high masonry and concrete dams. Of course, subsurface grouting lengthens the flow path of water under such a structure. It decreases I, and by Darcy's law, Q. Paul knew that not only from Arrow Rock Dam, where his crews had drilled 2 lines of holes 30 to 40 feet deep into bedrock beneath the structure and grouted one, more on the other one later, but also from the Lockington Dam, the one I showed in southwest Ohio, where his laborers had performed similar work, and they did their grouting there so well that no additional grouting was required for nearly a century. Paul also suggested that grouting could be performed by drilling holes to the depth required and grouting in reinforcing bars to be carried up and tied into the masonry or concrete to tie the dam and the foundation together. Now, those of you who have designed micropiles recognize that Paul's description matches their fundamental design. It's commonly understood that micropiles originated in Italy after World War II, but Paul's description suggests that the geohistory book needs to be rewritten a little bit on that count. Here's a photo of Paul's crews undertaking grouting at the Lockington Dam in the late 1910s. I'm not sure that their headwear would pass OSHA standards today, but you can see the mixing bucket and hoses. You can see the men hard at work, a few mugging for the camera. Compare that, with the St. Francis Dam in just a minute. Another method that Paul discussed was cutoff trenches, which he described as being excavated across the foundation along the upstream face of the dam. Per his guidance, they needed to be at least 3 or 4 feet deep and should be continued up the abutments and along the dam's full length. Structures on softer rock, he noted, should incorporate deep cutoffs or curtain walls of concrete at both their upstream and downstream faces. And he knew of what he spoke. Again, he had designed and constructed several cutoff trenches for dams along the Miami River in southwest Ohio. The final uplift prevention technique that Charles Paul mentioned was the construction of drainage galleries and uplift wells. And again, he knew this from experience. His crews, as I said, had drilled two rows of holes into rock along the foundation of the Arrow Rock Dam. They had grouted one of those rows, and the rest of the story is that they then used formwork to gradually extend the second row upward as the dam and its drainage gallery were built. These holes became uplift wells. And here's an example, picture being worth 1,000 words, of a cutoff trench that Charles Paul had excavated at the site of the Huffman Dam near Fairborn, Ohio in the late 1910s. And yet, contrast Paul's intricate, elaborate, and readily accessible guidance with the glaring lack of evidence that Mulholland et al. Even considered a grouting program. Mica schist is notoriously vulnerable to seepage, and yet they did not even consider this. As for a cutoff trench, a visitor to the site, a civil engineer, reported early in 1925 that there was no indication of such trenching up the hillsides to provide vertical abutment faces. At the center of the dam, the upstream portion of the foundation was actually excavated 8 feet shallower than the rest of the structure's footprint. It didn't even extend to bedrock. Now, Mulholland did include 10 uplift wells 2 inches in diameter beneath the center portion of the dam. But due to the length of the dam, that still left about 270 feet of structure on either side of those wells that was totally unprotected from uplift. Not coincidentally, right where the abutments were. Now, when I look at Mulholland's wells, it brings to my mind the lifeboats on the Titanic on its maiden voyage, because those were pretty much added to the ship so that the management could check a box saying that a safety technique had been employed, without regard for whether it would do the job in case of an emergency. Similarly, it seems like Mulholland's wells call to mind the idea of checking a box for safety and not meeting the actual purpose of uplift wells. Now, compare Charles Paul's photos of the Arrow Rock Dam and the painstaking excavation for that structure with the fact that here you have no cutoff trench at the east abutment of the St. Francis Dam because Mulholland did not incorporate one. All of which is to say that clearly this structure did not meet the contemporary geotechnical standard of care when it was built from 1924 to 1926 under the supervision of William Mulholland. And Mulholland made a couple of decisions that only compounded things as construction went on. He had, on previous jobs, engaged outside civil engineers as consultants to check him on his designs. This time, he did not. Now, Mulholland was legally exempt from an outside review of his designs. Under California law, municipal engineers were, and he was the municipal water engineer of the city of Los Angeles. But that doesn't mean it was prudent, even though it was legal. He also increased the height of the dam 20 feet during construction and never proportionately widened the base of the structure. Now, that did give him a lot more storage in the St. Francis Reservoir, but it made the arch of the dam thinner and more vulnerable. The structure itself was made of monolithic concrete, which was not uncommon for dams back then to lack reinforcement. I've seen no evidence that it was reinforced, but the unit weight of the concrete was just over 140 pounds per cubic foot. That's a little bit on the lighter side. And when you consider that they used hundreds of thousands of cubic yards of concrete, that missing weight adds up quickly. The dam was finally finished in June of 1926 at a cost of just over $1 million in money back then. Today, it'd be more like $23 million. And the 205-foot structure was initially filled, the reservoir behind the structure was initially filled so that it was about 55 feet below the dam's crest. The spring of 1927 was wet, and it actually rose to within 3 feet of the crest at that time, but nobody was unduly concerned, especially because the city and William Mulholland were now turning their attention toward the ongoing battle to build the Boulder Dam, now the Hoover Dam. It would supply the city not only with even more water to keep fueling its growth, but badly needed electrical power. Here's a photo of Mulholland proudly showing some dignitaries around the site of the completed dam. He is the mustachioed gentleman, second from right, pointing his index finger. And yet, not all was as positive as it seemed at the St. Francis Dam. As the concrete cooled, temperature cracks in the structure formed, and these leaked. Not worryingly, but they leaked. Now, the cracks in and of themselves were not problematic, but they reflected the fact that Mulholland had made lapses in his design judgment. He hadn't accounted for them. And even if he wasn't concerned about leaks through these cracks, he should have been concerned about the fact that it resulted in the loss of water that the city then couldn't use to generate revenue. But a much more worrisome problem emerged early in 1928. The rains that winter had been fairly heavy. Demand for water was down because the temperatures were cooler, and the reservoir slowly began rising. By the start of February, water was within 5 feet of the crest of the dam, and it stayed there for weeks and kept rising. By the start of March, it was within 3 inches of the crest of the dam, and it stayed there for over a week until the structure failed. Now, obviously, the difference in head between the two sides of the dam was going up, which meant that per Darcy's law, flow under the dam, Q, was going to increase. And in accordance with that, locals noticed in the weeks before the breach that leaks at both abutments were getting both more numerous and more severe. Word of the problems spread slowly by word of mouth and worried neighbors, until finally word got to the dam's keeper, Tony Harnischfeger, who reported to William Mulholland. On the morning of March the 12th, the day the dam failed, he called Mulholland, who promptly came out to the site with his deputy. Give him credit for that. Mulholland, the deputy, Harnischfeger, they toured the site. They observed the leaks that the dam keeper had noted, but the engineers weren't seriously concerned by that. So Mulholland told Harnischfeger to keep him updated, and he went back to Los Angeles. Here is a picture of Mulholland. Added a red arrow so you can see him. The contrast isn't great. Standing along the crest of the dam. The caption I read says this is the day of the failure, but it looks like that water is more than 3 inches below the crest, so I'm not quite sure about that. You can see him. The contrast isn't great, but standing along the crest of the dam, left for Los Angeles, the caption I read says this is the day of the failure, but it looks like that water is more than 3 inches. You can see from this water stage record, at around 8 o'clock in the evening of March the 12th, the water level readings at the dam, as measured at a gauge on the center of the dam at its crest, began slowly falling. Now, there was an outflow channel to take excess water away from the dam, but eyewitnesses did not recall leaks growing more severe then, which would have filled the channel. It wasn't around the time the sun went down, but you would think they would have at least heard that roar building up in the overflow channel. They did not. And that's because the truth of what was happening was even more frightening than that. The reservoir was so swollen that it was seeping more and more through the mica schist and slowly increasing the uplift forces on the dam. So this doesn't reflect a falling reservoir. It reflects a rising dam. And the problem slowly began to get worse. As you can see, more and more water began leaking. And by around 5 minutes to midnight, a large piece of the east abutment of the dam, labeled Block 35 in investigations by forensic experts, couldn't take the combination of uplift and high water any longer, and it gave way. And that created a nozzle through which water began jetting out from the reservoir. It's interesting to note, although no one at the time did, that Block 35 is right near where Mulholland's men dug that exploratory tunnel that they didn't grout for several years into the mica schist. After the fact, Tony Harnischfeger's body, the dam keeper, was found upstream of his home below the dam with a lantern in his hand. And that suggests that he had heard something in the final minutes of his life and went to investigate. But I'm getting ahead of myself. As Block 35 gave way, water percolating beneath the dam was also reactivating the old paleo landslide. And that was only exacerbated when Block 35 finally failed. When it failed, other dominoes began falling. Other blocks began failing in sequence. That removed support from the old slide. The factor of safety fell to 1, and the old slide was reactivated. It so happens that there was a power line running through that area, and at 11:57, employees at the electric company noticed that the power line snapped. Power went out. And that's because the slide had knocked out the pole. And because of that electric company's observation, we have data as to exactly when the St. Francis Dam failed. Now, a picture's worth 1,000 words. Here you can see block 35 in this area when it blew out, and how that nozzle of water, as I've said, caused a progression of failure of other blocks and also worsened the ancient landslide, until about a minute later, the ancient landslide came a-tumbling down. Other blocks were jolted out of place, and at this point, everything broke loose. After the slide and the failure of the east abutment of the dam, water poured through the structure's east side, leaving a trail of about 500,000 cubic yards of mica schist scattered like glitter through the San Francisco Canyon. Surviving evidence suggests that of the 205 feet of water depth from the reservoir, the uppermost 40 feet or so poured out through the east side breach. The waters were so powerful as they exited that they wrenched the center of the dam toward the east abutment. We know that because the water level gauge pipe mounted atop the center of the crest was bent toward the east abutment after the fact. And at that point, that wrenching action separated the dam from its west abutment, and that created a new breach through which water rapidly found its way as well. And this abutment also failed. Now, damage from this secondary breach was severe, but more features survived on the west side of the dam. For instance, a hairpin curve in the road right near the level of the full reservoir. And that reflects that secondary breach happened later. Now, the center came within a hair's breadth of failing during this time, but it stood. And the next morning, as the sun rose on the scene of the disaster, it loomed like a tombstone over the scene in a fitting, macabre way. Here's what that paleo landslide looked like in the mica schist after the dam had failed. And here is a diagram showing the path of the flood, which started in Los Angeles County and then progressed to through Ventura County, past Ventura and Oxnard, and dumped into the Pacific Ocean about 5.5 hours after it had after the dam had failed. So the disaster was awful. About 400 people died. That's our best historical estimate. We aren't certain. Fortunately, several telephone operators worked their switchboards, called houses up and down the valley in the middle of the night, and prevented an even worse catastrophe. But for William Mulholland, his career was effectively over. He had given Los Angeles 50 years of service, but it now ended ignominiously. And people wanted answers. The governor of California convened a panel of experts to get to the heart of what had happened, and Los Angeles County convened a coroner's inquest at around the same time. But this wasn't just a noble desire to serve the citizenry. There were political considerations at play here, because by 1928, the Boulder Dam was slowly winding its way through Congress, and it promised to add rocket fuel to the growth of the City of Angels. Now, all of a sudden, that was all jeopardized by the failure of the St. Francis Dam. It threatened to undermine confidence in concrete gravity dam design. Something had to be done to restore that confidence. There were fears, and they were effectively exploited by opponents of the Boulder Dam, that one morning it would break and the Boulder Dam would end up looking exactly like the St. Francis Dam did here. And here's that hairpin curve you can see in the road near the dam that indicates that the west abutment failed later than the east one did, where the roads washed out. And here's an even more dramatic view that shows the mica schist scattered through the San Francisco Valley like a trail of glitter. Now, the governor's commission on the dam failure was packed with heavy hitters. It was studded with civil engineering and geology standouts of the day. And these men, they were all men, got to work very quickly. They visited the site, they discussed their findings, and 2 weeks after the dam had failed, they delivered their report to the governor's desk. They stated that, in their opinion, the first thing to give way at the dam had been the sandstone at the west abutment because it had readily dissolved. But that explanation leaves a few things to be desired. It doesn't account for the abutment at the landslide at the east abutment of the dam. It doesn't explain why the hairpin curve at the west abutment of the dam was preserved, as I've noted, and as you've seen. And it also doesn't make sense in that case, why the discharge channel for the dam hadn't exhibited unusually high flows if water was leaking out. Plus, if the material at the west abutment had been as soluble as the panel had claimed, the abutment should have been exhibiting serious leaks throughout the lifespan of the dam, and yet there weren't any before March of 1928. Even the panel admitted that they weren't entirely sure about the precise sequence of events in the failure. As to the failure's cause, though, they were more secure in that. They blamed poor foundation design, i.e. Mulholland. But, and this is a large caveat, they added that the survival of that center section of the dam represented the strength of concrete gravity dams. Now, given how close that center section came to failing, as evidenced by an enormous crack in its base, that conclusion was more than a little disingenuous. But it's not necessarily false to say, as the commission did, that the failure of the dam reflects weaknesses on the part of concrete gravity dam technology in general. As I've said, Mulholland did not meet the standard of care. So they effectively blamed it on the engineer while finding exculpatory evidence for the technology itself. And that was exactly what the region's delegation in Congress needed to get Boulder Dam over the finish line. The coroner's inquest called a series of witnesses, William Mulholland among them. He is often remembered for his testimony that if there is any error in human judgment, I was the human and I won't try to blame it on anyone else. As he put it, the only ones I envy are dead. But not all of his testimony at the inquest was quite that noble. He insinuated several times that sabotage or an earthquake had felled the dam, even though there was no record of either. And he even at one point blamed an evil spirit that he called a hoodoo for cursing the site. It's unbelievable to me that the coroner's jury didn't call him out on that. A number of other engineers also made their way before the jury, one of them being Ralph Proctor, later famed for the standard Proctor test. It's worth noting that even as the coroner's jury was hearing witnesses, the governor's commission came out with its report. I don't know that you could say that the report necessarily was meant to influence the jury, but it certainly did. The jury felt quite comfortable with the experts who said that the west abutment had failed first. And that lent credence to the hypothesis of dissolving sandstone, or conglomerate as it's sometimes referred to in certain accounts, that plagues our understanding of the dam breach to this day. The jury was closer to the mark when it made note, in an irked way, of Mulholland's failure to engage outside engineering consultants. And here's Mulholland visiting the dam remnants after the failure. Now, whatever you think of the man, and I'm sure some of you have opinions by now, you can't help, or I can't help, but feel some pity for him in this moment. The lion in winter, about to cap off a glorious career, instead laid low by a tragedy worthy of Grecian myth. Now, it's worth noting not everyone ascribed to the West abutment failure hypothesis. Some prominent figures in the California water project scene had their own ideas on why the dam had failed, most notably Carl Grunsky, a civil engineer in Los Angeles, and Bailey Willis, a geologist at Stanford. They worked together on uncovering what they thought finding what they thought the real causes of the failure were, and then prepared separate reports that reflected their experience as civil engineer and geologist, respectively. Grunsky and Willis were the ones who formulated a failure hypothesis that focused on the dam's eastern abutment, and that hypothesis has been accepted by most subsequent scholars of the St. Francis Dam, myself included. It fits the surviving evidence better than does the hypothesis that focuses on the western abutment of the structure. And yet their work did not get widespread public attention at the time. A number of months had passed since the dam had failed. Readers had moved on to other stories. The governor's commission report had hogged the headlines for a while, and its conclusions had stuck. And ASCE didn't have much interest in bandying about the alternative theories because it wanted to avoid embarrassing the profession even more than William Mulholland already had. I don't think you could describe that as a whitewash. There wasn't some great rush to conceal the nefarious truth, as it were. But you can definitely say that the powers that were chose expediency over accuracy on this one. Now, even before the St. Francis Dam had failed, planning had been underway to form an international organization focused on dam safety. But the disaster only hastened its creation in the summer after St. Francis. ICOLD was formed, International Commission, of course, on Large Dams. That fall, William Mulholland quietly resigned as the water chief engineer for Los Angeles. He was treated with kid gloves in the press and by the public, but his peers privately scorned him, and he died several years later a broken man. With Mulholland out of the way, California's delegation in Congress had an easier time maneuvering the Boulder Dam through both chambers, and it was signed into law by President Coolidge just before Christmas, and easily makes for its own geotech history presentation. The following year, California tightened the requirements for professional engineers to oversee dam design. The municipal exemption that had allowed William Mulholland to do the work on his own was removed. And a few months later, the surviving center section of the dam was removed. It had become an embarrassing reminder of the disaster to the city. People would travel there as a day trip. Someone even died when they climbed up it and fell off. And so it was brought down with explosives. Now, of course, I could do another presentation about developments on dam safety since the St. Francis breach, but just a couple highlights are worth reviewing here. That dam engineering really emerged as its own subdiscipline of civil engineering in the mid-1900s. Combines elements, as you know, of structural, geotech, and hydraulic engineering. And by 1950, every state in the country had a civil engineering licensure law on its books. The days of a William Mulholland teaching himself how to be a civvy were dead and gone. Later in the century, work expanded to prevent future dam breaches globally through organizations like ICOLD, and domestically through organizations such as USSD, originally the US branch of ICOLD, and on the policy side, ASDSO. ASDSO was particularly successful at the end of the 20th century in lobbying for stricter dam safety laws across the states. And that number spiked in large part thanks to their efforts until 2 years ago, Alabama became the 50th state in our country to have such a law on its books. And in 2019, President Trump signed into being the St. Francis Dam National Memorial. Efforts are currently underway to build a visitor's center at the breach site. Fundraising for that effort is ongoing. But there are still some problems remaining with our dams today. On our most recent ASCE infrastructure report card, the country's infrastructure got a C, but our dams got a D+. The average American dam is now over 60 and doesn't meet today's best practices in design and construction. It's estimated by ASDSO that $165 billion would be necessary to upgrade non-federal dams, and the infrastructure bill chipped in some money for that, about $3 billion. But that's quite a bit from $165 billion, so more remains to be done. Meanwhile, dam disasters and near misses still happen sometimes. A number of years ago, Oroville Dam's spillway in Northern California nearly failed, and 200,000 people had to be evacuated. Fortunately, that turned out to be a preventative measure that didn't end up being necessary, but no such evacuation was given in a timely manner several years later for the double breach of two dams near Derna, Libya, that killed 11,000 people. So, what am I hoping everyone takes away from this? If you don't remember anything else, just really try to take some things away from these last couple slides. The story of Mulholland and the St. Francis Dam bears some powerful lessons. We need to balance confidence in our technical expertise and professional judgment with the recognition that we need to work together as a team to prevent mistakes, and the humility that we all make mistakes. To err is human. We have that limitation. And it's really true in geotech that we need that humility because of the high inherent variability of the materials with which we work. We have to meet the contemporary standard of care because it memorializes people who died either due to shortcomings in previous versions of the standard or flagrant violations of the standard. And as the standard improves, it's on us to keep up with it. We have to keep improving our design and construction practices. And while our work is very technical, its consequences in the end are human. The impacts of our successes might only be surpassed by those of our failures. As forensic engineer Roberto Leon has put it, a PE truly is a license to kill. As for the St. Francis Dam, it's sad to say that William Mulholland's handiwork didn't meet the standard of care. His team didn't conduct a detailed geologic study or subsurface investigation of the site. In fact, their tunnel into the mica schist at the east abutment likely contributed to the dam's failure. Mulholland did not incorporate adequate measures for seepage and uplift prevention into his dam's foundation, just a smattering of pitiful wells in the center of the structure. And he didn't have his crews properly excavate the foundations of the dam. I showed you the pictures of all the loose material and talus along where the abutments would be. And that was compounded by the fact that he operated free from outside oversight and that he raised the dam 20 feet during construction. Now, Mulholland's career spanned 50 years, and it was full of ingenuity and overcoming adversity and triumphing against long odds. But unfortunately, none of that erases his failures at the St. Francis Dam. If you look over the site today, with this story in mind, there is no pleasure to be had, certainly not on my part, in attributing the breach to William Mulholland. But that's where the evidence unmistakably points. As he once told onlookers when he opened the Los Angeles aqueduct, there it is. Take it. I'd like to acknowledge a couple groups of people. Geo-Institute, Virginia Tech, Sebastian Lobo Guerrero, my technical editor, Thomas Kemedy, who wrote an earlier version of this entry with me, and D.C. Jackson of Lafayette College, who literally wrote the book on the St. Francis Dam breach. And I dedicate this presentation in closing to the memory of the victims of the breach. Thank you all so much for listening. This time I'd like to open the floor for questions.
Thank you, Michael. Okay, so everyone, if you can put your questions in the chat, then as they come on, I can send them over to Michael. Mike, just out of curiosity, prior to the failure, Mulholland was a recognized expert, right? Was he given any credence because of that expertise? Certainly, after the dam failure happened, was he forgiven, or given the infancy of geotechnical engineering? Do they feel that maybe his work was somewhat okay?
Some people have made that argument, Jay. When I did my research using foundations, abutments, and footings, and read through some correspondence among Mulholland's peers, as excerpted in D.C. Jackson's book, and the practices of other dam engineers, again referenced in D.C. Jackson's book, unfortunately, it appears that I can't give Mulholland the benefit of the doubt on that one. It just seems that his workmanship did not clear the bar in terms of what most dam engineers were doing at the time. But I think that, as you said, the fact that he had this esteemed reputation led a lot of people to either silence their criticisms or have their criticisms be ignored by Mulholland in advance of the disaster. Got a question?
Yeah. Was there any evidence construction in the dam was rushed because of the extreme population growth of LA?
I mean, I haven't seen anything to answer the question that demonstrates that it wasn't rushed, but I also haven't seen any indication that things were expedited because of that. I think that if there was something that was driving the decision to construct it, at least, it was the fact that they were afraid of kind of sabotage and inability to access water from the Los Angeles aqueduct, which is memorably, if somewhat fictitiously, dramatized in the movie Chinatown.
It's my understanding that Mulholland's training consisted of reading engineering news record. With that, I can't imagine that landslide exploration was spelled out in detail in that particular magazine. Given in the 1920s, could they have properly identified the landslide risk?
It's interesting you mentioned that, because I talked about those geologists and civil engineers who had a different conclusion from the official report. They visited the site as well after the breach, and the geologist from Stanford, Willis, noted the old slide right away and said, "Oh, wow, that's pretty obvious to me." Now, of course, a lot of things are obvious in hindsight, right? There's no guarantee that that would have been noticed at the time. But what is certain is the fact that, given that there wasn't a thorough or even detailed geologic investigation of the site before the dam was built, that was all but certain to go unnoticed.
How long was the dam in operation prior to it failing?
For just under 2 years.
2 years. And you mentioned that there was a fair amount of seepage through the cracks within the concrete. Did they observe undermining of the foundations at all? Did they see any flux through that?
Not until right before the dam failed, not until those March 1928 leaks, that the leaks through the structure and the temperature cracks were noted and they were observed, but they were considered not considered worrisome either by Mulholland or by peers who criticized his work on other aspects of the dam. Mulholland actually had crews backfill those cracks with kind of tar-soaked rope known as oakum, which was common practice for backfilling such cracks at the time.
Okay.
So I think you can certainly question many aspects of Mulholland's work, but that particular aspect, I think he did meet the standard of care.
I see. Hey, folks, if you have any questions, feel free to type them into the chat, and we'll pass them along to Michael. Was there a spillway for this dam, being allowed to be within 3 inches of the crest? Was there any possible way to relieve the dam?
Yes, there was an outlet valve that could be opened through the center of the dam and funneled water into that channel that I mentioned. There was also a long dike along the west abutment of the dam that was paved in concrete. And if the dam it was a little bit lower than the dam, so if there had been a risk of overtopping, that would have overtopped first.
So could it have been possible that Mulholland made a bad call at his site visit when the dam operator showed up? If they would have taken the steps to open those valves and drop the pond level, could this whole thing have been avoided?
Very difficult to say it could have been avoided, but Mulholland's defenders have said that there's no way the lake could have been, or the reservoir could have been lowered very rapidly. But DC Jackson actually did the math and found that it could have been lowered by up to 3.5 feet over a 24-hour span, and that would have brought the lake back to where it was, or the reservoir back to where it was in 1927, where it didn't fail. So I think if they had taken swift and decisive action, there's no guarantee, but it would have been much likelier that the dam would have survived.
Right. You mentioned significant upgrades with the design and construction of dams after this failure. Were there any additional practices in notifying downstream population? Are you aware of anything like that? Did they have the ability, to let people know of an emergency
that emerged from this failure?
Yeah.
I do not know of any such reforms, although I think I should mention, Jay, that that's actually one of the few highlights of the St. Francis Dam stories, that there were enough telephones in service in the valley by the late 1920s that the operators were able to get on their switchboards and call everybody they could reach there. And it was a little bit impromptu, to be sure, but their notice no doubt saved hundreds of lives. It could easily have had double the number of casualties, if not more, had it not been for those phone calls. And as a result of all those operators and their diligent work, a lot of people who lost their property and homes and such were spared their lives.
Interesting. Okay. Well, I don't see any questions, so I'm going to kick this back over to Brad. Thank you, Michael.
That was fascinating. Really, really good story, and you tell it very well. I really enjoyed that. I think one of the most exciting things for me came right at the end when you told everybody what oakum was. My Oakham story is in the first house that we bought, I was redoing our master bath, which it was a 1,300 square foot townhouse. Using the word master there is maybe a little bit of a misnomer. I went to take out the shower pan and everything, and I couldn't do it. I just could not get it. And so I had to call a plumber in, and he came to me and he goes, "Have you ever heard of an Oakham joint?" And I said, "No." And he goes, "Well, nobody's used this since before World War II." And he explained to me the material and the process and everything. And so if people are not familiar with this, look it up. It's fascinating. I cannot believe, I mean, it makes sense that this was used to fill gaps, but on a large scale application like this, was absolutely incredible to me. So every detail of that was really good, impeccably researched. We really appreciate this today. So thanks for the great presentation, Michael.
Thank you for the opportunity.
I put in the chat for everybody a link. Well, it's just the link to the website, but you can read Michael's other posts on the Geotechnical History blog at geo-institute.org. We post about once a month. Sometimes it's a little slower, sometimes it's a little faster, depending on what's going on. But they are all over the place. They're not just all dam failures. They're not all at the same time frame, same time
not
period.
All failures either.
That is correct. Michael covers every aspect of geotechnical history, so you want to get over to the website and check that out. The other thing that he very, very nicely mentioned during his presentation is the ASCE Infrastructure Report Card, and I put a link to that in the chat as well. That comes out every 4 years, and you can check out what ASCE experts say about the state of America's infrastructure in several different categories. Of course, we would be remiss if we did not do one more reminder for you to head over to geo-extreme.org. That's geo-extreme.org. There you can register for the conference, find out more information, see what's going on. We would love to have you there in Long Beach with us at the beginning of November. It might even be more than love. You should go get registered and we'll see you there. Early bird registration ends September 9th, so get in and do it before prices go up. Great job today by Michael. Great job by Jay moderating as always. Our producer today was Aurora Flieger. You will want to be with us in 2 weeks. We have a little break before our next live stream. It's 2 weeks from today. We have our friends at Aldoa, the data management company, coming in to talk about managing and reporting geotechnical data. That'll be 2 p.m. Eastern on September 9th, same as it always is. So we'll see you then for another Geo-Institute live stream.